Hi guys, Mr. Johnny here. As I promised, you gave me enough feedback to motivate me to doing this video quite fast, so here it is. Video about this little board. So, the story behind it. I had a nifty little charger for a motorcycle battery for stuff like this. This one is 5 power, and that was a mains operated charger. Basically looked like a little wall wart, but then my buddy got a bike and we like to ride in the night time, so I basically gave him the charger to use. And that bike is, his bike is it's a typical pitfall of that kind of motorcycle, that it doesn't really charge the battery well if you ride at night. Of course, you ride with the headlight and you keep the RPMs rather low, so the charge rate is, the balance is not the best. The battery doesn't go dead, but it doesn't get charged enough. So the charger is there, but I want to get it back. He has a 24 volt DC power supply, so I designed this little circuit to suit that. This little circuit is a buck converter. It takes 24 volts DC, although it can use something like from 18 volts and upwards to something like 26, 28. The limitation is really here, the relay, the coil of this relay. Outputs around 13.8 volts, 13.9 somewhere there. Basically a float charge of the lead acid battery. Output current is around 1 amp, plus or minus 100 milliamps, somewhere there. Again, not critical. Constant current, buck converter with voltage limitation. Fully discrete, no ICs here. Has a reverse polarity protection and short circuit protection. Although the short circuit protection is kind of unnecessary because this thing is a constant current mode, buck converter. So by its very nature, it's not afraid of short circuits. It also has a diode on the input here. That's this part right here, which doesn't allow the reverse polarity on the input to fry this thing. You can see a few SMD parts. I usually use a couple of SMDs in the design. I don't go fully through hole or fully SMD because, what the hell. I use SMDs when it is convenient. When I need a very small design, or when I have a nice little dimensions like 40 by 50 millimeters and I can't really pack it up. With through hole I would have required some jumpers here, and so I just went and used a couple of surface mount devices. Okay, the schematic. Schematic is drawn rather poorly, but hang on with me, I will show you what it's for. The basic design is actually looks like it was a what was it? Constant current LED driver. It looked like it's basically a linear current source, current sink, if you will, which is driven into hysteretic operation. And that's your LED there. That's really all it was. It basically, via this resistor, some voltage was applied to the gate. The transistor was turning on, and when it was turning on, the voltage here will sag, and this will basically pull the voltage here on this base low, because the capacitor will act as a charge pump. It can actually pull this node below ground. In that very scenario, the transistor will be turning on, the current will be ramping up thanks to the inductor. It will not rise instantly. The inductor will limit the current rise. It will rise to a certain amount. When this voltage across this resistor, which is the current, depends on how much current, the voltage across this resistor will rise linearly proportional to the current, up until the point that this transistor will start turning on. And when it will start turning on, it will pull this gate to ground. The transistor will start switching off. The voltage here will start to rise. And basically when this voltage starts to rise, this capacitor will now basically allow current like that into the base of this NPN, switching it on very fast, which will switch off the MOSFET very fast. So the current here will look like it rises to the threshold, and it repeats like that. Typical DCM waveform. DCM because current is discontinuous. Current falls to zero on the next half cycle. And this one is a bit more complex. I added a totem pole driver to drive the MOSFET a bit more efficiently. Here it was active turn off, passive turn on. It was turned on by the rather high value resistor. Now it's driven with a totem pole cascade. It was powered from a 24 volts, so in order to not stress this zener, which is there to prevent the gate to source voltage from reaching dangerous levels, to the MOSFET that is, 12 volt zener. So if you'll just apply 24 volts signal here, this will apply almost 24 volt signal. This will apply almost 24 volts here. That will actually cause the current to flow through the zener. I don't need that. The zener is there to basically to protect from the spikes. So I just went and as you can see, added another 10K resistor. So this is basically a divider with a transfer function of 0.5, 24 volts here, 12 volts here. So when this totem pole is on, although the voltage here is 24 volts, it's a voltage follower. It follows the voltage on its input, which is 12 volts, so the output will be a little bit less than 12 volts here. This will not stress the zener, and this will turn on the MOSFET just fine, because the MOSFET is spec'd at 10 volts gate to source voltage. This transistor, which was here, now is located over here. As you can see, nothing has changed really. Instead of being connected to the gate, it's connected now to the input of the totem pole driver. Here's that feedback capacitor, choke. These are output terminals, your freewheeling diode. This capacitor is there to basically slow the operation down a little bit and to filter some ringing and other rubbish that may appear on across this resistor due to parasitic stray inductances and stuff like that. This slows it down just enough to actually avoid false commutations which will harm the efficiency. Efficiency of this one was around 78% or something like that. Around 80% under nice conditions. So pretty decent for a discrete design. Now, as for the voltage regulation, the current regulation here is similar to this. You get the idea. It just does not allow the current to rise above a certain value. So as for the voltage, it's controlled by this transistor. It has this LED in the emitter, which is actually kind of like a voltage reference. Here's how it works. Let's say basically the circuit starts oscillating like I told you it does here. It provides these pulses. Those pulses charge this capacitor. The voltage here, when the voltage here reaches the value high enough, it's kind of awkward because it's on the high side, but when this capacitor gets charged high enough, the voltage will start, the current start to flow like that through the closed contacts of the relay, if everything is right. So let's just imagine that these contacts are closed. It starts to flow like that through the LED, so it has to be green LED 2.5 volts plus the base emitter junction another 0.6 volts through here, and that will turn this transistor on. When it will turn this transistor on, the current will flow through the emitter collector junction, turning this transistor on and basically tripping this protection a little bit earlier, so it's gonna trip at a lower value. And so that's how that works. The reverse polarity protection. The contacts here are normally open, and the battery is disconnected from the rest of the circuit, really, majority of the circuit, until the voltage, the circuit shares the voltage here of the right polarity. When the voltage here with the right polarity is present, the current will flow through the base emitter junction of this transistor, through this resistor, through this LED again, so that will provide some voltage threshold, through this reverse polarity protection diode, so I don't stress the base emitter junction of the transistor with reverse polarity, and this LED which will go dead. Ask me how I know. It will flow here, turn this transistor on, which will allow the current to flow into the base of this transistor, which will turn on which will energize the coil of the relay, and that will close. So that, I hope that makes sense, because I'm not the... I appreciate your kind words, but I don't think my explanations are nowhere near perfect. So again, I do appreciate that you like my explanations and stuff, but of course they're not perfect. If you have some questions, leave them in the comments below. And yeah, my videos are not intended for a complete beginners. If you didn't get that already, it's they are for hobbyists, for hobbyists that have some background experience, so they will just will like to see some new circuits to check out and share some knowledge with each other. So that's that. Now, what it does if the... By the way, this capacitor is not connected like this. I took the positive and I connected it right here, like that. So if the battery is connected the wrong way around, this capacitor is not gonna be reverse biased. Now let me connect it up and you will see. So here we are. I'm gonna apply 21 volts from this, from the power supply. There are a couple of LEDs. That's the blue one, that's when the battery is connected right, and the green one is when the voltage regulation is in order, when the voltage is at basically constant voltage LED. That's what it is. Nothing glows until only this. See, the voltage regulation is working, the battery is not connected, so it's there, and we're gonna apply some damn it, where is it? we're gonna apply some voltage to the output with this battery that I showed you before. This one. Hang on a second, I will solder it up. Man, this video is gonna be a hassle to upload. But I don't know, maybe people like the long videos. Okay. Now, I'm gonna connect it up the right way around. I don't know if you'll hear the relay clicking because it's a silent, pretty damn silent relay. But watch the LED right there. I'll try to not block it with my finger, of course, that would be nice. I'm seeing you. Look at the blue LED. See, it went on. And unfortunately the circuit is DC, so it latches on. Because when the buck converter, when these contacts close, the buck converter now has the power and it charges this capacitor, and this capacitor now acts like a battery and it keeps itself together. But the nice feature is that this thing is so fast, in fact, the operation is fast enough that even if you turn it on nicely there, then put reverse polarity here, it still works, it doesn't fry itself. So here you see both LED are glowing. I'm gonna hook some load, you will see that the voltage is there. The bulb is glowing. Alright, I'm gonna show you the voltage. I hope. Stupid glare. There we go. Now the voltage. Come on. What the? Of course, it's on the amps, you dumbass! Johnny, you moron. Here's the input, 21 volts. The output, 13.8. Smack on 13.8. Now I like that. Alright. Now we're gonna... This bulb is actually large enough power to trigger the current limit, so the voltage with this bulb will be slightly less. 13.3. It's not that this circuit can't handle it, it's a constant current limit which is starting to take place. It is a 10-watt bulb. Now, I'm gonna cycle the power. The blue LED will go out. Alright. Now, if I'm gonna connect the battery wrong way around, absolutely nothing will happen. But in case, I'm just gonna focus on the board in case something juicy catches on fire. This contact is positive, this contact is negative. Here you can see where the positive output is. I'm gonna connect negative to positive. Oh, convenience. So convenient. Ugh. Mamma mia. If you think that this video is pain to watch, you don't. This video is even more pain to make. No sparks, nothing. It's connected there. The battery is not dead. See? Wait, you saw that it's not dead. Now we're gonna turn it on. The LEDs actually might be just bright enough so you can see it from the other side. Right here you will see a faint blue glow. There, yeah, you can see it. Now I'm gonna reverse polarity it. At this point in time, this does put a stress on the freewheeling diode quite a bit, but it still works. I have tested it like that, like 20 cycles, and it works. The surge current still flows, but mostly into the capacitor. You will see some sparks, but are actually bugger all sparks. The LED went out, the blue one. But what's more important is now that I connect it right way around, it will come back to life, and I will show you the output voltage again. Here it's glowing again. Let's put this battery away before I short it out and create some smoke. Let's show you the voltage. $13.74. The circuit is not very temperature stable, so don't mind that small difference. And it still lights up just fine. And so you can see that it's indeed a buck converter. I'm gonna show you the output current and the input current. Let me solder it up. Okay, here am I. I'm gonna connect this emitter in series. You can see 0.45 amps. Here are my hands, and 0.35 amps there. So the current on the output is larger than on the input because the voltage on the output is smaller, is lower than the input. Again, the efficiency is right around 80%, 78, 80, depends on input voltage and output current, stuff like that. Works good enough. Basically, it will work just fine for this heatsink to be more than sufficient. Okay. Holy schmidt! 23 minutes. Alright, that's it. I hope you appreciate my effort, because it's gonna take a bloody hell long time to upload this monstrosity of a video. Now I can actually encase it and give it to my friend and take my power supply, my charger back. So you will actually, and I probably will make a video about that as well. Next stuff, well, actually I have to repair the TV that I showed you. There. Then I can work on the CDR. I do have some parts for it. Namely the MOSFETs and the half-bridge driver, which is used to drive the MOSFETs. It's not my name there, but I still blocked it. Oh well, thanks for watching, see ya.